In this section and the next two, we'll be talking about a family of geometric figures called conic sections. The conic sections include the circle, the parabola, the ellipse, and the hyperbola. We've already talked a little bit about the circle. There are several approaches that can be used in studying conic sections. The Greeks used an approach having to do with the emergence of these conic sections from the intersection of a plane with a double-napped cone. Now take a look at this figure and I'll give you an idea what that means. This is a double-napped cone. It's a cone with its reflection. And if you imagine a flat surface intersecting this, that is maybe straight across like this, then the figure for the intersection would be circular. You see, it would be something like that. And if you tilt the plane like this, you would get an ellipse. And if you tilt even farther, you would get a parabola, and then up and down like this would give you a hyperbola. Now that's the way the Greeks studied the situation. We could take another approach. Another approach might be purely algebraic, where we had kind of a general form for the equation associated with each of these. But really there's another even more intriguing way to study the conics, and it's the way that we're going to approach them. And it is from a very geometric standpoint. And we're going to define all of the conic sections in terms of distance, and then associate an equation that relates distance into those conic sections, and we're going to be able to construct graphs and so forth. Well, as I mentioned, we've already talked about the idea of circle in a previous chapter, and we talked about equations for circles, and you know that the circle is defined as the set of all the points in a plane which are the same distance, that is equidistant, from a single point called the center of the circle. So hence the idea of definition involving distance, and that's what we're going to feature here in this whole study. Okay, let's talk about parabola. Now, you know we've talked about parabola in the past, and the parabola was simply the graph of a quadratic equation, and we studied all about how those graphs change with changes in equations and all that kind of thing. Well, we're taking a completely different approach here. The figure is the same, but the equations will look quite a bit different. And our definition for parabola is pretty different as well. We're thinking in terms of distance now, and all of our definitions have to do with distance. And the definition for parabola goes like this. Suppose we start with a point and a line. Now the point is not on the line. The line is called a directrix, and the point is called a focus. And the parabola is all the points in the plane that are the same distance from the focus and the directrix. That is, we have a point right here midway, you see, between these two, and we have another point like this distance and that distance are the same. We have another point over here such that this distance and that distance are the same. We have another point out here somewhere where this distance and that distance are the same. And all such points compose our parabolic curve. So the parabola then would have this kind of shape. And it's the shape of parabolic curves from before. There's no surprise about the shape of it. The surprise is the introduction of focus and directrix. Now the point right in between the focus and directrix, this point, which is the lowest point on the parabolic curve as I've drawn it here, it might be the highest point if I drew it like this, but it's called the vertex, as we have talked about in the past. We could also talk about a line of symmetry here. If we drew an imaginary line right down the middle of it sort of here, a line containing the focus and the vertex and perpendicular to the directrix, then we would have a line of symmetry, and sometimes this is called the axis or the axis of symmetry. To begin our study, we're going to think about situating this parabolic curve on a coordinate plane in a particular way. We're going to think about the vertex as being located at the origin. So we'll have a configuration like this. Now, we're structuring it this way just to introduce the equation associated with this parabolic curve. And it's a really strange looking equation. It goes like this. Now, when the parabolic curve opens up or down, the equation associated with it looks like this. It's x squared equals 4py. And the reason for having the 4 in here is to allow us to identify the distance between the vertex and the focus. And you know, if we have the distance between the vertex and the focus, we automatically have the distance between the vertex and the directrix, because the directrix is just the same distance on the other side of the vertex from the focus. All right, now it's the p-value that is the distance from vertex to focus, and it's a directed distance. That is, this p-value, it can be positive or negative. Usually we just assign positive numbers to distances, but now we're going to call this a directed distance, because it's a distance that has direction associated with it for the value of p. If p is positive, then the direction is up, and negative, the direction is down, as we'll see in just a few minutes. Okay, so the 4 is in here just to accommodate this idea of identifying the value for p. Now notice, x squared equals 4py. The x squared is isolated on one side of the equation. Now in this study, we're not restricted to the idea of function. You know, we can have relationships between variables that are not function relationships. When we study the circle, for example, it fails the vertical line test, so certainly we're not talking about a function. But in this study as well, we're not restricted to the function idea, so we can have parabolic curves that open to the side like this. Now, here's our focus, here's the vertex, and here's the directrix. And the equation associated with this is y squared equals 4px. Now, notice just the swap of the role of x and y here when the graph kind of opens to the side. I want you to also notice that the parabolic curve tends to wrap around the focus. So it wraps around the focus in this direction. If the focus was over here, then the curve would look like this. And when we're talking up or down, if the focus is above the vertex, then the parabolic curve opens upward like this. And then if the focus were down here, it would open downward. All right, let's see how we would deal with the equations. Suppose we want to construct the graph associated with this equation, which is the equation for a parabola. Now you recognize the equation for a parabola because we have a second degree variable. One of the variables is second degree and the other is first degree. As we continue our study here, it's going to be increasingly important for us to be able to recognize what kind of figure we're dealing with early on in the problem. And that's the way we recognize parabolas. So we have a parabolic curve, and the prevailing characteristic for the structure of our equation, and this is the equation of a parabola whose vertex is at the origin, is what we're really dealing with right now. The prevailing characteristic is that the variable squared is isolated on one side of the equation, and so we'll manipulate the equation to that form. Well, the standard form also calls for us to have a factor of 4, a distinguishable factor of 4. And so what we're going to do is force the factorization of 4 out of the 10. You see, we're going to just snag 4 out of the 10, whether it wants to come out of there or not, whether there's a 4 factor in there or not. And we do that like this. We can say, okay, 4 times what will give 10? Or we might say 4 times 10 fourths. You see, is equal to 10. And so I'll put 10 fourths here, and now I'll simplify that. But that's the technique we use to force that factorization. This is 5 halves. Now we identify p as being this 5 halves, or 2 1/2. Now that gives us information about distance from vertex to focus, and so we can structure our graph. And it's just a sketch. But here's how we make the sketch. Now, at this point, you may be thinking, wow, wait a second. We have parabolas that open to the side and parabolas that open up or down. How do we know what kind of parabola we have? Well, that's an interesting question. We have to know which way we go from this origin. We know the vertex is at the origin, and we know that the p-value is positive. It's 2 1/2. So we're going to go in a positive direction. But do we go along the x-axis a positive distance of 2 1/2, or do we go along the y-axis a positive distance of 2 1/2? Well, there are a few ways to be able to tell, but here's a pretty good way. If you have a second degree x, and a first degree y, then it implies that one value of y will produce two values for x. So one value for y, let's say that one, will produce two values for x. And then because of that, we have this opening either up or down. Now with a p-value that's 2.5, it's positive. We know that the parabolic curve is going to open upward because once we find that, see here's 3, so 2.5 would be right here. There's the focus. The curve tends to wrap around that focus point, so the curve then would look like this. And the directrix would be the same distance on the other side of the vertex. So there's the position of the directrix. Now we're just going to be sketching graphs here. You know, we were very careful about sketching graphs very accurately when we studied parabolas before, when they emerged from quadratic equations. We wanted a precise graph. We used the calculator on them and all of that kind of thing. And we could do that here too. In fact, we could make a table of values and plot a bunch of points and discover exactly the behavior of the graph. But really, our study is more concentrated on the manipulation of the equations in a certain form in order to discover the structure of the graph, and not so much exactly how abruptly the curve will occur on the coordinate plane. I will tell you this, though, that as this focus point moves away from the vertex, the parabolic curve tends to sort of lay down. It tends to be more gentle. And as this point gets closer to the vertex, it tends to have a more abrupt kind of graph. Okay, here's another one. Now notice y squared plus 5x is 0. And once again, we see that we have a second degree y, first degree x. So one variable second degree, the other variable first degree. That means that we have a parabolic curve. The way that we deal with it is to isolate the variable squared on one side of the equal sign. Now I've done that here by subtracting 5x on both sides. Now the technique is to force the factorization of the 4. So we go through that thought process like we did before, that 4 times what is negative 5, you see? And you can always identify it by just writing this. Negative 5 over 4, you see, because those would cancel and we would have negative 5. Now simplify this. Well, it's pretty easy to simplify. It's quite simply negative 5/4, which is negative 1 1/4. Now, how are we situated on the coordinate plane for graphing purposes? Well, we have a first degree x and a second degree y. That means that one value of x will cause us to have two values for y. So one value for x, say out here, gives us two values for y as points on the graph. That gives us a curve that opens to the side. Now I don't want to imply that they all open to the right, because certainly they don't. It could be opening to the left. The x we chose could have been here and the y's like this. But it's right or left as opposed to up or down. All right, now we look at the value of p to decide the position of the focus. Now our vertex is here at the origin. Our p-value is negative, so that's the negative direction, left or right, 1 1/4. Let's call this 1 and this 2, so 1 1/4 would be about right here. So the opening then, which tends to wrap around the focus point, looks like this. And the directrix is the same distance on the other side. So it would look like that. Now, in this study, as we have seen a few times in the past, that from a teaching standpoint, there are sort of two directions for this study. One direction is where we take an equation and produce a graph, and the other direction is where we take information about a graph and produce an equation. And this next problem is like that. Suppose we want to write an equation of the parabola with vertex at the origin and focus at 2, 0. You see, so with this information we're going to produce the equation. Now you begin maybe by just sketching the graph. If we've got a coordinate plane and we know that the vertex is at the origin and we have a focus at 2, 0, then we know an awful lot about the nature of this of the graph. We know that the graph tends to wrap around the focus, so we know we have a parabolic curve that opens to the side, and it's opening to the right, and we know that this distance is the p-value, so p is equal to 2, and it's a directed distance, so it's positive 2. We know that the directrix is on the other side. It's over here, a distance of 2. It's not really important to our problem, but we could complete the graph like that. Now we're ready to structure our equation. Now here's what we're noticing. We're noticing that one value of x, or any of the x values along here, are producing two values for y. So we have a y squared situation. So the nature of the equation is y squared equals 4px. Now we've identified the value of p, so y squared equals 4 times 2x, or y squared is 8x for our equation. We could put this in a different form. We could kick the 8x to the other side if we want to and write it as y squared minus 8x equals 0, but I think this is appropriate as a simplified form for the equation corresponding with this information. Now we're going to talk about the equation of the parabola when the vertex is not located at the origin. But it turns out it's pretty easy because we're going to use the same technique that we used with circles. You may recall that when the center of the circle was at the origin, the equation was x squared plus y squared equals r squared. And the center was at the origin. The radius, of course, is r. Now, when we move the circle's center away from the origin, we introduce the idea of an HK. H and K are, the HK represent the coordinates of the center, and in the equation we find them in binomials that are squared. So it's x minus h squared plus y minus k squared equals r squared, and the center is at h and k. An important characteristic here to notice is that h and k are numbers that follow minus signs for the identity purpose for the h and the k. Okay, so that's the idea with the circle, and it's the same idea with the parabola. We start with the notion that we have an equation associated with a parabolic curve whose vertex is at the origin. Now, when that vertex moves away from the origin, we just introduce the idea of an h and a k. The h is associated with x and the k associated with y, and we make a couple of binomials here. So as the vertex moves away from the origin like this, we have an x minus h squared and then 4p times y minus k. The vertex is at h and k, and the focus is at h and then k plus p, and let's see why. You recall now that p is the distance from the vertex to the focus. So if we're talking about the coordinates for that focus point, then it would be the same horizontal component you see for the vertex. It would be the h, and then it would be this distance plus p. So it would be k plus p, you see. Now, I don't think it's worthwhile to memorize this. As a matter of fact, I don't think it's worthwhile to memorize this. I think it's worthwhile to remember that and then extend the idea of this into that idea. You see, and it cuts down on the things that we have to sort of recall by rote memory. We just memorize, I guess, the idea of this x squared is 4py. And then we just introduce the notion of h and k. And by doing that, by going through a little thought process like that, we can almost generate our own equations. For example, if we're thinking about a parabolic curve that opens to the side, then rather than try to just outright remember the equation associated with this, we can generate it ourselves like this. We can think, okay, we have a parabola that opens to the side. It means that one value of x is generating two values for y. That means that the y is squared. So if this parabolic curve were located at the origin, that is, if the vertex were at the origin, we would have a y squared equals 4px. Okay, so that's the basis upon which we're working. And now, because we're justifying the parabolic curve away from the origin, we introduce the idea of h and k. And the h is associated with x and the k is associated with y. So this becomes then y minus k squared equals 4px minus h. You see, so now here's the equation associated with that one. We could talk again about the coordinates for vertex and the coordinates for focus. Of course, the vertex we know is at HK. And we could generate some kind of relationship for focus like this. We could say, well, let's see now. The focus is at, from here we go a horizontal distance which is equivalent to the h and then plus p. So, oh yes, it's h plus p, and then the vertical distance is the same as the vertical distance for the vertex. So it would be k. Consider this problem. Suppose we want to generate the equation associated with this information. We have a vertex at 3, 2, a focus at 1, 2. That's all we know about the problem, but we want to generate the formula or the equation associated with this. We begin by just sketching a little graph. So we think like this. Okay, we've got a vertex at 3, 2. We have a focus at 1, 2. All right, vertex, focus. We know that the curve tends to wrap around the focus. If that's the focus and that's the vertex, then we have this kind of behavior for the parabolic curve. We know that the directrix is out here, but we don't need that information in order to construct the equation. All right, now we just kind of start this thought process. It's the notion that, let's see, we have 1x generating 2y's. So we have the notion of y squared equals 4px. All right, but we're not located with our vertex at the origin, so we introduce the idea of h and k. H associated with x, k associated with y. So we have the y minus k squared equals 4p x minus h. And now, with the information that we have here, it's pretty easy because we just identify, let's see, the coordinates of our vertex were 3, 2. So h is 3 and k is 2. So k is 2. Now notice that the k is following a minus sign here, as we would expect. And then we have 4 times the p value. Let's see. Distance from vertex to focus, from here to there. Now we're talking horizontally, and so from here to there it's a directed distance, so it's negative 1, 2. So this is negative 2, and then this is x minus the h value is 3. And we would probably just multiply these and clean up a little bit. We could actually expand it a great deal, but if we want to leave this in a pretty much standard form, then we would probably write it as negative 8 times x minus 3, like this on the right side. In this next problem, we start with the idea of an equation. And let's say we want to construct the graph. And let's also say that we want to generate the coordinates for the focus. Okay, so we would begin like this. We would think, well, I know because of this binomial squared and this binomial involving x that the vertex is not located at the origin. I know that the vertex is at hk, and let's see, h follows the x and k follows the y, and they each follow minus signs. So the vertex is at 5, and we think of this as minus negative 1/2. So negative 1/2 for the k value. All right, I know that much. But wait a second, I need the p value. Oh, it's found right in here. So we need to use a step to identify the value of p, and we do that by forcing the factorization of 4. So we think 4 times 2 over 4 Now we see that the p value is 1/2. Okay, so p is 1/2. Now, with that, let's see. Vertex at 5, negative 1/2. 1, 2, 3, 4, 5. This is negative 1, so negative 1/2 puts us right here. All right, now, which way are we opening? There's the vertex, but do we open left, right, up, or down? Well, let's see. The y is squared and x is to the first degree. So 1x generates 2 y's. We're opening to the side. Okay, now do we open this way or do we open that way? The value of p will help us with that. P is 1/2. Aha, that's a positive 1/2. So from here, horizontally, positive 1/2, we go over to this point. And the parabolic curve tends to wrap around that point. And the vertex and focus are pretty close here, so I know that the parabolic curve is going to look a little thin. So it's going to look something like this. And now we can identify the coordinates of the focus pretty easily. Let's see, we go over 5½ and then down 1/2. So the focus has coordinates 5½ -1/2. And what about the directrix? You know, the directrix is the same distance on the other side, and sometimes you might be called upon to write the equation for the directrix. And let's see, it's a vertical line, and vertical lines are x lines, and they are x lines at a particular distance from the y-axis, and that distance is 1, 2, 3, 4½ So this line is x equals 4½ as the equation for the directrix. Well, in this next one, we have an equation that is in general form. It's kind of in an expanded form. We don't know anything about the graph by looking at this equation. So we have to manipulate it into standard form in order to read the information we need for graphing purposes. Now to do that, here's what we first think. We see that we have y squared and x is to the first degree. Now that tells us we have a parabolic curve, and it tells us about how to situate the terms on one side of the equation or the other. We're going to put the terms involving y on one side of the equation and all the other terms on the other side. Here's what we're thinking. It's y squared plus 6y. Now I'm going to leave a space here, and on the right I'm subtracting 8x on both sides. Whoops, I'm subtracting 8x on both sides, so I'll get negative 8x on the right. And I'm subtracting 25 on both sides, so I'll get this. Now, you're probably anticipating I hope you're anticipating what I'm going to say about this, because we've seen it before. We have to use the technique of completing the square here in order to cause a condition of a binomial squared over here. And as I say, we've seen it before, so we know the technique. And the technique is to identify the constant here that can be associated with these two terms to cause us to have a trinomial square, which factors into a binomial squared. So we are completing the square. We are completing the trinomial square. All right, half of 6 is 3. 3 squared is 9. So we're adding 9 over here, but we're causing an imbalance in the equation. To maintain the balance, we have to add the same amount over here. So we're going to add 9 on the right side. Now back over here we factor, and as expected we get y plus 3 squared. On the right, well, let's see, we're collecting and so forth, and we get negative 8x, and then negative 25 plus 9, that's negative 16. All right, now what? Well, gee, we have a couple of things to do over here. And one thing we ought to realize, and we need to realize in beginning the manipulation on the right side, is that the form that we're trying to take is this. It's y minus k squared equals 4p times x minus h. And one thing we know is that we're going to have to force the factorization of 4, but there's a subtle situation here we have to deal with, and that is that in this parenthesis, the understood coefficient of x is 1. So before we deal with the 4, we need to deal with that binomial involving a coefficient of 1. You see, a binomial involving x with a coefficient of 1. So that means we need to factor out this negative 8. You see, before we go looking around for that 4 business. Okay, so here's what we do. We bring down the left side, and we yank this negative 8 out of these two terms. Now, it's convenient here because 8 is a factor of both of the terms, but even if it weren't, we would have to force the factorization of whatever this coefficient turns out to be. So we have negative 8 times x. Let's see, negative 8 out of negative 16, oh, that leaves plus 2. Now we go about identifying the p-value by forcing the factorization of 4 out of the negative 8. So 4 times negative 2 times x plus 2. Now we have all of the ingredients that we need. We know that we have a vertex at hk. Now h follows a minus sign and it's associated with x. So this is x minus negative 2. So negative 2 for the h value, and the k is here, minus negative 3, so negative 3 for the k value. And we have a p value of negative 2. Now let's sketch the graph. Let's come back this way. Let's see, the vertex is at negative 2, negative 3. Here. Okay, now how is the graph situated? Well, we will go back over here and we see, oh, second degree y, first degree x. So 1x gives rise to 2 y values. Again, we're opening to the side. Okay, so we're opening to the side. That means that the distance p is taken as a horizontal distance, and that p value is negative 2. From here, let's see, the positive direction is that way, negative direction this way, so we go to the left 2. All right, here we go. Now, the graph tends to wrap around the focus from the vertex, and so that graph maybe looks something like this. All right, now, what about the coordinates for our focus? That might be something that we would be after in a problem like this. And let's see, it would be negative 1, 2, 3, 4, and then down 3. So negative 4, 3. Now, notice I'm reading this off of the graph. I'm finding the coordinates of the focus from the graph rather than trying to think of some algebraic method for doing this. We could generate an algebraic method easily enough, but it causes us to have something extra to remember. And so just looking at the graph makes it a lot easier. In this problem, the equation seems all jumbled up. Notice that we have the x squared on the right side. We have y on the left side. Gee, this is a very general form for the equation. Now, to make the adjustment, to put it into this standard form where we can see aspects of the graph, we begin by noticing that x is squared here and y is to the first degree. So we want the terms involving x on the left side of the equation and all the other terms on the right. So that's the first thing we do, is take these two terms and kick them out of the right side. I'm adding 1/2 x squared and adding x on both sides to give this. I'm subtracting y on both sides, so I get minus y plus 1/2 on the right. Now I'm thinking, well, gee, I have fractions here. I'd like to clear those. So I'll multiply through by 2. And multiplying by 2 causes this leading coefficient to be 1, which is kind of an important aspect when we complete the square, as you may recall. So 2 times this term gives me this. 2 times x, 2x. 2 times negative y, negative 2y. And 2 times 1/2 is 1. Fractions are gone. All right, here we go. We want to complete the square on this side. So we think, well, what do we need to add here? Half of 2 is 1. 1 squared is 1. So we add 1 here, and to maintain the balance of the equation, we add 1 on the right side as well. Factoring here, we get x plus 1 squared. Over here, collecting the 1s, we get minus 2y plus 2. Now, we have to create that situation over here where we have a binomial involving y, and the leading coefficient is 1. So we force the factorization of the negative 2 out of these two terms. So we pull negative 2 out of this term, we're left with y. Pull negative 2 out of this term, we're left with negative 1. Now we need to force the factorization of 4 out of negative 2. So we write negative 2 as 4 times negative 2 over 4, which becomes negative 1/2. Now we have the value of p, and we have the h and k for identifying the position of the vertex. Now remember, h and k, numbers that follow minus signs, the h associated with x and the k associated with y. So we have an h of, let's see, x minus negative 1. So we have negative 1, 1 as the coordinates of the vertex, and the p-value is negative 1/2. With that information, let's see, vertex at negative 1, 1, the p-value negative 1/2, we identify the position of vertex, and then we think, oh, how are we opening here? So we look back, we see that the x was squared. So we have one value of y giving off 2 values for x. So we're opening up or down. Now, from this point then, we're going to move up or down the distance of negative 1/2. Oh, that's down 1/2. So here's the focus, and the graph looks about like this. Once again, we could identify coordinates for the focus and an equation associated with the directrix if we want to do that. Well, once we have studied as much as we have with the parabola, there are some aspects of the parabola that can be studied farther, and in geometry mostly these matters are discussed, and it involves a little bit of vocabulary. If we take a couple of points on the parabola and connect them, and if that segment goes through the focus, then that's called a focal chord. So here's an example of a focal chord. A segment joining a couple of points on the parabolic curve and going through the focus, a focal chord. Now a special focal chord is the one that goes through the focus, but it is perpendicular to the axis of symmetry. Here would be that focal chord, and I want to emphasize the perpendicularity here, and this is called the latus rectum. I think, though, the most important geometric characteristic involved in parabolas is this. And what I mean by parabolas is I mean parabolas as we're studying them, parabolas with this focus point. This focus point is very important in business and industry because it provides us a way of manufacturing things like satellite dishes and automobile headlights. Here's what I mean. There is a reflective quality with parabolas that works like this, that if we have a signal that comes in from, let's say, this direction, a signal will bounce off of this parabolic curve, and now I'm thinking of a satellite dish, a three-dimensional satellite dish, comes into the dish, bounces off of the dish itself, and bounces right at the focus. So the signal could be here. The signal could be here. You see, and this is the way signals are picked up with satellite dishes. They use this reflective quality of the parabolic curve to do that. And the receiving unit is right here at the focus point. All right. Now, in a similar way, the reflective quality works in the other direction as well. With automobile headlights, the dish, once again, is a parabolic kind of dish, and we have a focus point identified, and the light source is placed right here at that focus point. And then the light is emitting, the light emits from this source, and it hits the glass reflection of our headlight, and it goes onto that piece of glass on the parabolic dish, and out this way, and out this way, and out this way, you see? And that's how automobile headlights are made, and all of these use the idea of this reflective quality of parabolic curves.